Welcome back. So this is part 2 of linear independence and spanning sets. So here we are back into the definition of linear independence, and what we'd like to do now is to revisit an example of in the vector space of matrices, specifically matrices that have 3 rows and 2 columns. So this is typically denoted as M sub 32 or M32. And in this vector space, remember all those 10 properties are satisfied, and there are 2 operations, scalar multiplication and addition, and there is closure, and there's a lot of good stuff happening. So here there is a very concrete example. So this is a set with 1, 2, 3, 4 elements. These elements of this vector space are here called vectors in the sense that they are members of vector space. They're two-dimensional arrays, they're matrices. And so the question is, are these vectors as members of a vector space, are they linearly independent? Is this set a linearly independent set? So we have to go back to the definition, right? So we write a relation of linear dependence. So we write these elements as a linear combination that is equal to 0, but equal to 0 on this vector space. So in other words, we're going to consider a scalar multiplied by the first vector, first element of that set, scalar multiplied by the second element, a scalar multiplied by element number 3, and another scalar multiplied by the last one. Now, this would be a relation of linear dependence provided that this equals to 0, to the 0 vector in that vector space, and that would be the 0 matrix. Okay, so this looks pretty much, we could think of S as being a set with elements U1, maybe I use the same notation, but anyway, U1, U2, U3, and U4. And so by making that consideration, what we're writing here is something that looks like alpha 1, U1, and then alpha 2, U2, and alpha 3, U3, and then alpha 4, U4. And this is equal to 0, where 0 is the 0 element, the 0 vector in the vector space. Of course, it's a linear combination, right? So this is adding up. And in this vector space, for these matrices, we're talking about 0 being a matrix that has 3 rows and 2 columns. So this would be the 0 of the vector space. This vector space is M sub 3, 2. 3 rows, 2 columns, right? So there is the linear combination we would like to consider. And that linear combination is something we have to work out using the matrix operations or properties of matrices. So it's certainly matrix operations. What's happening is that by carrying out, for example, here, this first matrix is going to be a matrix that it contains this scalar everywhere. So this is 2 alpha 1. And the first column looks like 2 alpha 1, alpha 1, alpha 1. Sorry. And the second column, so this first matrix looks like with first column 2 alpha 1, alpha 1, alpha 1, second column 0 minus alpha 1, and then 3 alpha 1. If we do the scalar multiplication on the second term of this linear combination, first column looks minus alpha 1, minus 4 alpha 1, minus 2 alpha 1, minus 2 alpha 1. Second column looks 0, 2 alpha 1, negative 6 alpha 1, right? And so that's what's happening on every term of this linear combination. And then by adding, this is 1, 2, 3, 4 matrices. Each of those scalar multiplications is a matrix. And that matrix has 3 rows, 2 columns. So we end up with a matrix with 3 rows, 2 columns, which is what we have here. and this is the 1 1 entry, right? And we obtain that by adding up all the 1 1 entries on those 4 matrices. So there we collect 2 alpha 1 minus 4 excuse me, that was alpha 2 here in the second matrix, minus 4 alpha 2 plus alpha 3 minus 5 alpha 4, and so on, right? So then what we do next is to compare this to the 0 matrix, right? So as that linear combination on the left side of that first equation, which is a matrix equation, becomes a 3 by 2 matrix on the left side, and that is compared, well, not compared, it's equal, is equated to the 3 by 2 0 matrix of zeros, okay? And so what goes next is to compare entry by entry. So for example, we can compare here in the left side, the matrix on the left side, this entry is row 2, column 1, so this is the 2, 1 entry, and that entry is compared to the 2, 1 entry on the matrix of zeros that is on the right side of this matrix equation. That would give us an equation that would be alpha 1 minus 2, alpha 2 minus 2, alpha 3 minus 10 alpha 4 equal 0, right? So that gives us one equation. But hey, we have 3 by 2, so there are 6 entries, right? And each of those is equated to 0, so there will be a set of 6 equations, okay? And that set is nothing other than a homogeneous system of equations where alpha 1, alpha 2, alpha 3, and alpha 4 are the unknowns, right? And that set of equations looks like this. So we have 6 equations and we have 4 variables or 4 unknowns. So we would form the matrix of coefficients. So here we write the matrix. So essentially we write this homogeneous system in matrix vector notation, right? So the variables here are alpha 1, alpha 2, alpha 3, and alpha 4, and that is compared to the column vector with 6 zeros. And now this is very familiar territory for us. So this is very standard. We form an augmented matrix. We could, in this case, this is a homogeneous system, so you could work with simply this matrix. This is a 6 by 4 matrix, and you can draw reduce, and basically you aim at computing the solution set of this system of linear equations. And it happens that the RREF here has this form, and then we know that there are non-trivial solutions for this homogeneous system of equations. So this implies linear independence, linear dependence, right? So that set that we were exploring, the values of alpha, we can find non-trivial values. So not all values of alpha have to be 0. There will be non-zero values for alphas, such that the linear combination is true. And therefore, we would classify this as a set that is linearly dependent.